Assalamu alaikum, dear students. We are going to talk about astronomy and cosmology today. And although it's a big topic in itself, but your syllabus deals with some very basic ideas about various properties of stars, like how luminous a star is. So we start with the definition of luminosity. Luminosity means the total energy emitted by the star in all directions per second. So this is energy emitted per second by a star. We usually denote this by capital L. This is a very important property. As I move through various other topics, you will see that luminosity plays a very important role uh, in calculating various other things. For example, we'll be able to calculate the surface temperature of stars, we'll be able to calculate the size of the stars, uh, how uh, what is the distance of that star from the earth. So all these calculations become possible once we know the luminosity of a star. And how we know the luminosity of star, there are techniques. For example, there are stars there are stars in our universe with known luminosity. We have used various techniques to calculate the luminosity of various stars, and these stars are known as standard candles. uh, Sun is one of those stars that we know the luminosity of, so it plays the role of a standard candle. And if we know the luminosity of a star, how we find the distance of that star, that is another idea, and that is called radiant flux intensity. Radiant flux intensity means I is equal to luminosity of a star divided by 4 pi d square, where d is the distance of that star from us. This means you are here on this spherical surface. This is a three-dimensional surface, and you are here. This is the earth, and this is the distance of earth from the center of this star of known luminosity. So let's say this is sun. So if this is sun and this is the distance we need to work out, I should know this luminosity, and I should know the radiant flux intensity, which means how much we are receiving on earth every square meter, right? So this is intensity, how much energy we are receiving every square meter per second. Intensity, you know the definition of intensity. So using the luminosity of the sun, I gave you the value of luminosity of the sun is approximately this is of the order, luminosity of the sun is of the order of 10 raised to power 26 watt. So if I use this value here, and this is the fraction that is also given in the question, you can easily find the distance of the sun from the earth, which is nearly 150 million kilometer. After this, we can move on to another important idea, which is used for calculating the surface temperatures of the stars, and that is known as Wien's displacement law. Wien's displacement law. This law tells us how we can estimate the surface temperatures of any object if we know what is the radiation it is emitting. For example, Wien's displacement law tells us that when we increase the temperature of an object, it emits various wavelengths, various photons of different radiations, each have its unique wavelength, and the graph with intensity and wavelength appears to be something like this. This is where we have maximum lambda. Lambda max means for this particular wavelength we have maximum intensity, which means most of the light emitted by this hot object has this radiation, this wavelength. And for example, for sun, let's say if the surface temperature of the sun is to be found, we know what is the dominant radiation that the sun is emitting. Lambda max for sun is nearly 500 nanometer, which is yellow light. And if I use this yellow light in this formula, lambda max multiplied by surface temperature of a sun, this is nearly equal to a constant which is known as Stephen's constant, and its value is 2.897 into 10 raised to power minus 3. If we use this value, the temperature comes out to be approximately 6000 Kelvin. So this is the surface temperature of the star, which we have easily worked out because we know what is the predominant wavelength the sun is emitting. So that means from the simple idea of the wavelength coming to us, we have worked out how hot the surface of the star is. Next comes the size of that star, and we can easily use that using another idea, and that is known as Stephen-Boltzmann law. Stephen-Boltzmann tells us that luminosity of any star depends on two factors. The formula is 4 pi sigma r square T4. Sigma is a constant. This is known as Stephen-Boltzmann constant. This is the radius of the star now, of which the luminosity is known, and this is the surface temperature like the one we have just calculated. Suppose I want to know the size of the sun now. For this I need to know the luminosity of the sun, and luminosity of the sun is 3.85 into 10 raised to power 26. This is equal to 4 pi, and sigma is a constant which has value 5.6 into 10 raised to power minus 8. This will of course be given in the formula sheet. This is Stephen-Boltzmann constant. R square is to be found. So R square is to be found, and the surface temperature, suppose we are talking about the sun, so its surface temperature is 6000 Kelvin and raised to the power 4. If I simplify this all, it should come out to be nearly 700,000 kilometer, which is the radius of the sun. So these are very, very basic calculations of your topic, and if you practice a few questions like this, you'll be able to cover approximately half of the syllabus.